Hi, current and prospective MASH users. My name is Melissa Pergandy, and I'm a postdoctoral associate in the Yang-Ga Research Group at the University of Wisconsin-Madison. In the following video tutorial, we will briefly cover how to add post-translational modifications, also known as PTMs, to a protein sequence in MASH native. It is important to note that this video tutorial is intended to be used in parallel with the step-by-step instructions found in the Getting Started guide, which is located in the Documents folder in your MASH native software package. In this video tutorial, we will walk through Tutorial 5, Post-Translational Modification Analysis using UniDec within MASH native. Please pause this video and download the necessary data file to your computer and save it to a new local folder as described in the Getting Started guide, if you have not done so already. The goal of this tutorial is to define the PTMs on a selected protein, NADH dehydrogenase ubiquinone iron sulfur protein 5. First, we will perform a deconvolution and assignment of charge states using UniDec in MASH native. Second, we will assign PTMs to our protein sequence until we match our observed results. Shown here is the main MASH native interface. In MASH native, use the import data function in the targeted mode node to import the thermal raw data file, which we have downloaded for this tutorial. To do this, first select the thermal raw data file type. Next, select the downloaded MS data file that you have placed on your local directory and click OK to edit. You should now see the raw MS data file for ECD fragmentation of precursor mass to charge 886. To continue, we need to perform a deconvolution. To do this, select the deconvolution function in the targeted mode node. When we do this, the process wizard will be shown. Here, select the UniDec deconvolution algorithm. Once we have done this, we can then input our deconvolution parameters. In the General tab, the precursor mass to charge 886 is already shown. Enter 14 in the charge state. You can then push the tab button on your keyboard and the calculated monoisotopic mass will be shown. Next, we need to select ECD for the activation method. This is done in the bottom left corner. Once you have done this, click the Deconvolution tab. Here, enter the deconvolution parameters as shown on your screen. We will need to change the max charge to 30 and the bin sampling to 0.1. After these settings have been entered, go back to the Basic tab. Here, click on the Start button to run the deconvolution. The status of the analysis will be observed in the Workflow Manager. Once the run is complete, the queued workflow box will be empty. The workflow will then be shown in the Completed Workflows box. Once the deconvolution is completed, you can close the Workflow Manager to view your results. You will see that the mass list in the center panel automatically populates with our deconvolution results. Here, users can manually review the isotopic peak fit for each, as discussed in previous video tutorials. We can now paste the sequence for our protein in MASH native. To do this, copy the protein sequence from the Getting Started guide, click Characterization in the Targeted Mode node, and then paste your protein sequence. The protein sequence will then be shown in the right panel in MASH native. The mass of the sequence will also populate below the sequence. Observe the most abundant mass, noted as 12,479.4474 Daltons. We can go back to our mass list and compare our measured results with the most abundant mass from our pasted spectrum. When going through the mass list, we see that we have peaks that have most abundant masses of 12,346.4004 daltons. With this, we can look for known PTMs that we can add to our sequence to match our mass list. To do this, we can go to uniprot.org and search for our protein by entering the name and species. Once we have found our protein, we can look for reported PTMs. Here we see that there are two disulfide pairs reported, C33 and C66, as well as C43 and C56. With this information, we can go back to MASH Native and add these modifications. To do this, we can go to the configuration dialog, which is found under the Tools menu. Once in the configuration window, we can then click the Modifications tab. Here, we can add our modifications. In the empty box, type disulfide into the name category. Next, type the monoisotopic mass and average mass of minus 1.0078 and minus 1.008 respectively, and then press enter. The new modification can now be seen in the list. You can now select OK to close the window. Knowing the locations of our disulfide bonds, we can now place the modifications within our sequence. Before doing so, enlarge the sequence table by dragging it to the left. Once the sequence table is displayed, add the disulfide modifications. Start by clicking on C33. Once C33 is highlighted in red, select the PTM drop-down box and choose the disulfide modification. Repeat this process for C43, C56, and C66. We can now see that with the modifications, our most abundant mass has changed in the sequence table. With the PTMs included, our most abundant masses are still not matching our mass list, so these cannot be the exact PTM or PTM combinations on our measured protein. We can clear our PTMs by selecting Clear All Modifications under the sequence table. With our modifications removed, our sequence table shows the most abundant mass of our raw sequence again. If we look at the difference between our sequence mass and our selected mass in the mass list, there is a difference of 133.047 daltons. A very common occurrence to consider is the cleavage of the N-terminal methionine. To edit the sequence, click Characterization under the Targeted Mode node and then paste your sequence. The sequence dialog will be open, and we can now delete the N-terminal methionine. Once removed, click OK. With the methionine removed, in the sequence table, our most abundant mass has changed to 12,348.4069 daltons, very close to our selected mass, but not quite equal. We are still seeing a difference of 2.0055 daltons. From our UniProt search, we know that this protein is known to have disulfide bonds in the sequence, which correlates to the loss of 2 protons per disulfide bond pair. With this, we can add 1 disulfide bond pair. In the sequence table, we can select 2 cysteines from the UniProt disulfide bond locations to add our modifications. Here, I am selecting C43. Like before, we can select disulfide bond from the PTM drop-down box. We can then repeat this process for C56. Note that the position of these cysteines is 1 less than the original position due to the removal of the methionine. With both of our cysteines modified, we can then select Show Assignments. Now, our most abundant mass correlates with the results observed in our mass list. With this, we can infer that this is the correct combination of PTMs observed on our protein. It is important to note, though, that in order to determine the exact location of the disulfide bonds, we would need to evaluate the MS-MS spectrum. When done with your analysis, always be sure to save your results using the file function in the upper left corner. This concludes our short video tutorial series for using MASH Native. Please see our Getting Started guide and user manual for more details on the use of MASH Native.